So, in this episode, we want to prove that there are infinitely many prime numbers. So, in this episode, we want to prove that there are infinitely many prime numbers. So, to be clear, prime number is natural numbers that is bigger than 1 and only have two divisors, which are 1 and itself. So you can see some of the beginning, earliest prime number that occur gonna be 2, 3, 5, 7, 11, 13, 17, 19, and 23, etc. Okay. By contrast, composite number is natural numbers that is bigger than 1 and have more than two divisors, which mean 3 or 4 or 5 or even more divisors. So composite number can be 4 or 6 or 8 or 9 or 10, 12, 14, 15, etc. So we can see that, for example, number 15 gonna have the divisors like 1, 3, 5, and 50 itself. So there are a total number of 4 divisors for the number 15. So it is a composite number. But here our goal is to prove that the set of prime number p here is infinite. So even though in general the number of prime numbers is it's quite sparsely distributed in the number line, there are infinitely many prime numbers. So now we're gonna prove this statement. So we're gonna prove by contradiction. We're gonna use the method of proving by contradiction. So we're gonna assume a contradiction with the statement that we want to prove. We're gonna hypothesize the statement A. There are finite numbers of prime numbers. So this is exactly the opposite of our desired statement. So we gonna prove that statement A is wrong. That's gonna be our goal. Okay, so how we gonna prove statement A is wrong? So we're gonna first assume that A is true, and then we're gonna try to create a contradiction where we follow along the realization that A is true. We're gonna create a contradiction, so A must be wrong. So let's suppose that A is true. So then P will have a finite number of elements. Okay, because we suppose that the number of prime numbers are finite. And let's us order P in the increasing order and denote the largest prime F. Okay, so you can see here P is gonna be equal to the set of 2, 3, 5, 7, 11, 13, 17, etc. until the last prime F. Okay, and now we're gonna denote C as the product of all elements in P. So C is the product of all elements in P. So C is 2 times 3 times 5 times 7 times 11 all the way to F. Okay. Since we assume that there are finite number of prime numbers, thus P has a finite number of elements. Obviously, P has a finite number of elements. And C plus 1, C is the product we are considering, will not belong to P. C plus 1 will not belong to P. Well, that's obvious because C plus 1 is greater than F. So C plus 1 is not a prime number. Okay? So because P is the set of all prime numbers, that is our hypothesis. C plus 1 doesn't belong to P, so C plus 1 is not a prime number. That is understandable. And you can see as C plus 1 is bigger than 2, and the fact that C plus 1 is not a prime number makes C plus 1 a composite number, right? That's obvious, because if you are not a prime number, then you are a composite number if you are bigger than 2. So therefore C plus 1 is divisible by at least one another prime. Well, this is really true, because any composite number gonna be divisible by at least one another prime. For example, 24 when it be divisible by 2 and 3, 28 gonna be divisible by 2 and 7. Okay, so C plus 1 will be divisible by at least another prime. Okay. However, C plus 1 is in fact not divisible by any other prime, because you see, you look at the equation for C. C is a product of all the prime, and so if you add 1 to C, which is C plus 1, when you divide the C plus 1 to any prime at all, the division will always have the remainder of 1, because that's obvious. So therefore, our hypothesis A, there are finite number of prime numbers, create a contradiction. The contradiction is that C plus 1 is divisible by at least another prime, and C plus 1 is at the same time not divisible by any primes. Therefore, our hypothesis A, there are finite numbers of prime numbers, is wrong, because it creates a contradiction. So therefore, the opposite of the hypothesis A is true, which is there are infinite numbers of prime numbers. Therefore, we prove what is necessary.